This video, E2, is one of the longest, if not the longest, and basically because it covers an awful lot of territory that I do hope you find interesting. Now, previously we mentioned that to operate a motor, you need to have a disconnect, overcurrent, control, and overload. And as you find out, if we're talking overcurrent fuse protection, a disconnect inevitably comes with it. If you're using a disconnect switch by itself because the motor is remote, then that disconnect is doing nothing but serving as disconnect. Now, overcurrent, the purpose is to basically stop the current flow if there's a short circuit condition. The expression often used is crowbar, like pretend somebody dropped a crowbar across the conductors and they shorted out. In fact, some people refer to it as short circuit protection, and that in some ways may be a better description. When you're looking at overcurrent, you got three things. Number one, at what current level do we trip? We can't have it trip at a very low current level or be tripping all the time. So at what level do we trip? How much current can the device actually stop? Now you say, okay, well, as soon as the contacts open, current can't flow. Well, the contacts may be opening in such a way that they strike a bit of an arc, which ionizes the air, which allows conductivity, and in fact, it hasn't stopped the high current flow, okay? So there's the question, how much current flow can the device actually stop? Known as peak interrupting rating, IP for current peak. And last, after initiation, how long will current flow before it is stopped? In other words, how much power does it let through? Total let through power being I squared times T. Appreciate that AC systems are easier to interrupt than DC systems because the reversing current flow tends to help stop arcing. Now, fuses. Fuses, basically a link, whatever, that melts under high current. Once it hits a certain level, it will actually melt it, if not vaporize it completely. And the element within the fuse is surrounded by silica sand, which helps dissipate, get rid of any arcing that occurs. Now, one of the things in motor applications, basically, as we saw before, you do get a roughly 6 times interruption, say 5 times because of losses through line, when a motor goes to start. So we don't want it tripping unless the motor locks up and we do need to kill it. But if the current gets really bad, a dead short, we want it to go fairly quickly. So dual element fuses, required to both rapidly trip at very high current flows, say 10 to 15 times rating. Let's say it's a 100 horse motor at 600 volt, which is 100 amp. So now we're talking like at 1,000 to 1,500 amp. If we hit those kind of levels, for sure we want it to trip, but we don't want it to trip at say 5 times at 500 amp, okay? Otherwise, if we start a motor across the line, every time it's going to take out the fuse. By having 2 elements, one for the lower current value and one for the very high current value, both these requirements can be met. Now, if you take a look at this little graph on the right-hand side, and sorry, the way it prints, there's just no other way of doing it than the way it shows up. But anyway, if you look at 30 amp, which is the bottom line, at 10 times current, which would be, the example here, I think 150 horse motor. So let's take 150 horse, or pardon me, a motor that's pulling, 175 amp, okay? At 175 on starting, and if you follow the little arrow there at 175, where it hits at point B, that fuse will give you 10 seconds before it trips. So at 175 amp, which they divide again, 175 divided by 5 means you've got a motor of about 35 horsepower at 600 volt. Okay, so to start, the fuse will not trip for up to 10 seconds at 175 amp. But let's say you've had a dead short and that amperage has doubled. In other words, we're about 10 times, and we're up at 300 amp. At 300 amp coming over to point E, we're going to trip in 1/10 of a second. In other words, it happens pretty rapidly. The comment being, by the way, the expression dual element has been replaced nowadays by time delay, whatever you call it. But the concept is valid and the fuses really didn't change, just the name. Interrupting current. Now, one of the fuses can deal with very high fault currents because basically the fuse element in that quartz sand will just disappear at very high currents. Okay, and the silica sand will help dissipate the amp. The problem is that the switch, the disconnect switch, which is allowing you to change fuses and serve as an isolating current, that disconnect switch will have a much, much, much lower rating, maybe 10,000 amp, which means the switch is unsuitable for manual operation or remote tripping, what they call shunt tripping, if a significant fault exists. There actually have been stories of people, a short occurring, the fuses disappearing, somebody in the process of doing it, somebody runs over, hits the switch to turn it off, but the disconnect switch itself causes arcing, and by doing so, the enclosure becomes electrified, and the poor person trying to flip it gets electrocuted. It has happened. Second question, the amount of current let through actually with a fuse, again, because it can literally eliminate the current flow path for a fair distance, they go very quickly. Less than half a cycle, which means 8 milliseconds or less. And as you can see with the little drawing here, it's quite a bit less. You can see the arc starting up to the top, the half cycle, and it's letting go fairly quickly. And if you take that peak times the time squared, that's the amount of power that is let through, which is not very much. Now, circuit breakers. Most circuit breakers are what they call thermomagnetic, which means that they actually have two different ways of tripping, one for low current values and one for high. The thermal part is for low current rating, and low current demand. If you look at it, you see there's the line goes beside a bimetal element, which means the more current the line is handling, the more it heats up, the more that little bimetal element will start to bend because it's bimetal, and eventually will hit the trip bar, which unlatches the contacts, which are spring loaded, unlatches those contacts, and the circuit breaker has tripped. Okay, but that action works great, say with a motor or something, and gives you some time to play. If it's a very high current, the element is not quick enough. So what they do is they have a second trip element, which is basically a core and a magnet, and simply the magnetic force created by that high current will bring over a piece and trip the bar directly. Doing it that way, it can trip within one cycle, which is about 16 millisecond. Now, circuit breakers, the interrupting capability is usually under 100,000 amp, usually quite a bit under. And I'll make the comment that most applications, pump stations and whatever, the fault currents, and there are ways of calculating them, I won't get into it here. That's your homework, figure out about fault currents, maximum fault currents. But fuse element, as I say, you can add a fuse to a circuit breaker, which is kind of a hybrid, and then you get your high interrupting. But breakers are relatively more in the 40,000 amp, okay, which, as I say, is adequate for a lot of applications. They're compact, capable of reset, and suitable for manual operation. In other words, if it's a 40,000 amp rating, it doesn't care if it's tripped by either thermal, magnetic, or manual, going over and flipping it, it can handle it, okay? Which makes them good for remote shunt tripping, which is used for things like ground fault, whole other field. They also have one screaming advantage. If they trip, you simply reset them. You don't need to have another fuse available, and appreciate, particularly in remote locations up north or whatever, you probably won't have the necessary fuse. Now, you can also get non-automatic circuit breakers, which literally are just a disconnect switch and can be used as such. In other words, you can have a non-automatic breaker at a remote motor and it's considered suitable for disconnect. Another variation of circuit breaker is MCP. Realizing that the thermal part is essentially to prevent overload situations. And in houses, that's quite common in the table saw, whatever. If you're dealing with municipal motors, whatever, you will have overload relays. That overload relay takes care of the lower current overload tripping. Therefore, you really don't need it in the circuit breaker. So a variation of a circuit breaker is an MCP, which is basically a circuit breaker without the thermal element, but with an adjustable trip electromagnetic element. You can set where it actually trips at. Electrical code refers to them as instantaneous trip circuit breakers and permits the use only with starters having overload protection. By the way, that adjustable trip, my son ran into a situation where they had a job, and every time they went to start a motor, the motor never even got to move. It just seemed like they turned the motor on and the power to the motor was shot immediately. To find out that the trip adjustment screws were set way down to the point that even the starting load of the motor was too much, bang, instantly, a fraction of a second, it's gone. Now, you being adjustable up to about 13 times motor full load current. That's as far as you can go with them under Canadian Electrical Code. An initial approximation we used to use is go 10 times. So in other words, if you've got a 50 horse motor at 600 volt, that's 50 amp. So set it at 500. In paradise, you adjust them till they trip and then they go a little bit above. Most of the situations you haven't got that kind of time. So setting it at 10 times current rating is a good average. The maximum trip time is 1 cycle, 16th millisecond. So they do go quickly. And the fact is, they say they can be set close. If you're really worried about peak current let through or peak current and let through power, you can set it down to where exactly it should be. I've thrown in the bit about how they're operated because to me it is a big deal. There are 3 basic mechanisms to manually operate a switch, a fuse switch, or a circuit breaker. The first is fixed lever. You got a lever attached to the enclosure directly, and when you open the door, it's still in the same position. So even with the door open, if you're testing something, if you hit that switch, bang, it works. Okay. The next option up is slide handles. This is actually something that Westinghouse, which became Cutler Hammer, which became Eaton, developed, and I'm a big fan of, and I think they're still around. Basically, what it is, it mounts right on a circuit breaker, not a switch, but a circuit breaker, even if it's unfused. It mounts to it, and when you open the door, it is still there. It can be tripped back on if you want to test for current, but if you have to kill it, bang, you can do it very quickly just by slapping the top of the handle. Here's pictures showing what we're talking about. This picture on the left, you can see on the right-hand side of that enclosure, there's a strip, and on it is the lever operated for the main disconnect for that panel. And if you look slightly below center of the panel, you see kind of 2 cream-colored things. Those are the slide handle mechanisms for each of 2 motors. And again, if you look at the picture on the right, there's the slide handle mechanisms on. And to turn them off, all you have to do is hit the top of them, bang, they're off. They can be padlocked off, by the way. That little thing on the handle to the right actually will pull out and you can padlock it if you have to. We'll get into that issue of disconnect or padlocking in a minute. The third option is lever and rod, where the mechanism fits on the circuit breaker in most cases, and it has a rod sticking out which matches a lever mounted to the door. The problem with those is actually 2. The simple problem is that when you go to close the door, if you've got several motors, in other words, several of these switches, you got to get them all in line to close the door. So it's a nuisance. The bigger issue is if the door is open and you are checking currents with a meter, if something goes wrong and you want to kill that thing, all you're dealing with is a stupid rod. And if you're good and tough and brave, you can grab the rod and twist it. Most of the time you use a crescent wrench to flip it, and you probably don't have one at that particular moment. Here again is showing pictures of what we're talking about. The very top of the enclosure, you've got 2 levers, okay? And as I say, when the door is opened, that mechanism comes with the door, and you're just looking at a rod. Like, look on the right-hand side. At the very bottom of that thing, you can see a gold-colored rod sticking out with a little red dot beside. That is the rod that is mounted to the switch breaker behind it, And that's what you have to deal with if you've got the enclosure open and something goes wrong and you want to trip it off. Now, one of the things, if you're servicing equipment or electrical, if you have a disconnect, you want to make sure that while you're working on the equipment, somebody doesn't come up and flip it on. So what you basically do, the intent is to padlock that. And in construction sites or municipal operations, the idea is that everybody has their own padlock. And you probably can only get one padlock on the mechanism, but you can get devices like we see here, which allows you to have umpteen devices on it. So everybody has their padlock on it, and the only way you can get the power back on is to get everybody who's put a padlock on, will be working on equipment, to take the padlock off. So everybody's happy. Everybody knows that power's going back on. By the way, a lot of sites, organizations, if you try to defeat that mechanism, like you could grab a hacksaw and cut it apart, that's ground for dismissal, and the unions usually don't argue at all. And of course, with two T's, we know what lotto is. That's a way to lose money real quick. The T, the lotto, the LOTO, lockout, tagout. The tag is a labeling process when you're using lockout. To be honest, if it's a short-term item, probably won't. But anything significant, yes, you have a tag. And what it does, it says why the lockout is there, explaining why, the time of the lockout when it was done, and the name of the authorized person who attached the tag and lock. And only the person who placed the log and tag to begin with is the one permitted to remove them. This procedure makes sure the system cannot be started without the authorized individual's knowledge. Now, little side issue, ground fault protection. You've probably got this at home. These little breakers that will trip if something shorts out a little bit. Basically, what happens with a neutral grounded system is let's take a look at this little drawing on the right. You can see on the left there's a 120 volt power supply from a transformer. Ignore the GFCI for the moment. You got a hot conductor going over to motor and then coming back, and of course you say power goes back and forth. What happens if that, quote, hot conductor wears against an enclosure such that the enclosure becomes that line? Basically, if somebody walks up and puts their hand on the enclosure and they're standing on the ground, they give the power an alternate path. It can either go through the motor, which is a load, or it can go through that person who put his hand on it. And putting one hand out through his heart down to ground, you can see the consequences and the fear. So one of the things that came about, we're talking about Faraday's law, where if again, power is moving through a magnet, you can energize, create magnet by having power move. Okay, what's happening here is the GFCI basically is noting power is going one direction. The same power should be coming back. If it does, it basically just a big coil. It does not see any power being generated because where there's current flow one way, there's a current flow to opposite going the other direction. When one direction exceeds the other, then this thing will start to generate power. And very sensitive electronics will note that, and immediately there's a trip to it, and it will trip off, and you're safe. If it's literally high enough to save a person's life, which is the intent, it's known as Class A ground fault protection. Lower classes for ground fault are really to protect the equipment from damage. Okay, and that's where you see like the use of devices that are detecting that and using shunt trip to shut off breakers. But if you're looking at personnel protection, it must be capable of tripping at 10 milliamp within 2.7 seconds per Canadian Electrical Code, blah, blah, blah. And any outdoor receptacles shall have that, even if they're high voltage. Know of a case where a treatment plant had outdoor high voltage receptacles, I think they were 600 volt, and they did not have ground fault protection. Interesting, it became provincial law under the code, but this had been put in, and it basically you were allowed 1 year to implement that requirement. It hadn't happened yet. This happened where something shorted out and somebody was killed over it. So this stuff is serious. Now, overload protection. We've been through disconnect, we've been through overcurrent. Overload, which means the motor is overloading, and what you want to do is trip it before the poor thing gets burned out. Essentially, an overload relay must trip in less than the number of seconds defined by the class at 6 times the trip current rating. So it's always what we're talking about in seconds is based on the assumption you're 6 times the current. In other words, a 100-horse motor at 600 volt, we're talking 600 amp. Now here, for example, if you had a motor with no service factor drawing 100 amp, it must by code be protected by a device that will trip at 115 amp, okay? However, the time it takes to trip, in other words, if the trip point is, we're looking for 100 amp, at 115 amp, you're allowed 15 amp, the device must trip within that 6 times. And the time it takes to trip is inversely proportional to the overload. Now I lie there. They're 100 amp. That's okay. That's our motor at 100 amp. So the device has to trip at 15. You're allowed 15% gap in between. At 6 times the current rating, which is 690 amps, if you have what they call a class 20 device, overload device, it must trip in less than 20 seconds. Okay, and I apologize for that screw up on the rating there. We're talking about, as I say, 100 amp motor, 115 amp is allowed. You can operate at that free. Anything beyond that, the trip time is inversely proportional, and at 6 times, essentially, it has to trip within 20 seconds if it's a 20-second device. Now, classes, you can get class 5, class 10, class 20, class 30, and each one is spelling out the number of seconds that's allowable before it trips at 6 times the current rating of the device. Now, class 10 and 20 are the most common in the kind of stuff we deal with. All equipment with moderately high starting load should have class 20. For example, we'll get into it later, drainage pumps require class 20. Soft starts require class 20. For other applications, most centrifugal pump applications, class 10 overloads will provide better motor protection. In fact, with submersible motors, they require you have class 10 protection. Again, that means at 600 times current, times the operating current, it has to trip within 10 seconds. Less is okay, but within 10 seconds. And you look at the curves here, a conventional melting alloy relay at 6 seconds, you can see it's tripping at just under 20. At the far right, where there's 6 times, just a hair under 20 seconds, it's tripping, so it's class 20. Now the next one, if the same situation except for using a class 10 overload, at 10 it will actually, within 10 seconds, it would actually go 4 times the current, and at 6 times, it will trip in only 6 seconds. So there's the advantage of the class 10. It is quicker tripping, so the motor's not seeing that high current for near the time. Now, thermal compensated. What that means is you could have the situation where the motor, and these things are thermal, most overloads. You're getting more and more solid state now. Classically, before, they had a bimetal trip element, and basically the current was run through a little heater. So the higher the current, the hotter it got, the quicker it tripped. The problem being that you're worried about what the motor's seeing, not the overload. If they're at the same temperature, no problem. But what happens if the overload is in a nice cool area and the motor's at an area very hot? Well, then that motor is going to see more of a situation. What we really want it to do is act strictly on the current. So where that motor current flowing through resistant element, the option to that is going to ambient compensated, which means the trip setting is relatively unaffected by ambient temperature. It can be a cold room, it can be a hot room. Basically, it will trip on the current, not so much the temperature. And that can be done with thermal devices or with solid state devices. This is a very important little drawing. Starting current. When a motor is locked, in other words, a motor can't turn. Pretend you've got a The output shaft of the motor's got a big crescent wrench on it, and Hercules is holding it down. When a motor goes to start, the initial locked rotor current, because when a motor goes to start for a fraction of a second, it isn't moving, and the inertia of it and its load will keep it there for a fraction of a second. So you can see we've assumed here there is some line loss. In other words, not 600%, but line loss. And the motor, because the voltage has dropped off a bit, is 500 times. And this is typical of motors. So we're seeing this very high current when it's locked. At that same situation, zero speed, the current is quite high. The torque is high. We did the current, pardon me, and the torque is also very high. So we got lock rotor current and lock rotor torque. As the thing speeds up, the torque will go up and then come down the green line to a point where we're operating at full load torque, and at that RPM, that's the horsepower we require. Horsepower being a product of RPM and torque. And you can see how the current falls off. So at that point, the current ends up being at 100% rated. In other words, if the old classic thing, if it's a 100 horse motor at 600 amp, lock rotor current will be about 500 amp, operating current will be about 100. So this is typical of most motors. Now, the nice thing is that centrifugal pumps generally start very quickly. Okay, very low initial load. The pump itself, a centrifugal pump, remember the affinity laws? Zero speed, zero power required other than the drag of the bearings. So virtually zero at zero speed, and they're very low inertia. Centrifugal pumps, even with the water in them, are relatively low. In fact, the motor rotor itself is the major inertia load that motor is seeing. Therefore, most pump motors will start very quickly and minimize locked rotor current heating. You get very high things, we'll get to in a minute, if you've got very high inertial loads, like starting a conveyor belt. But the centrifugal pump is fairly quick and dirty. Now, the next item, control. And basically, contactor. If you take a contactor and add an overload relay, which is the way it is usually done, put the two together, it becomes an ACL, across the line starter. Okay? If we add the necessary overcurrent protection to that starter, in other words, we've taken the contactor and overload with a circuit breaker or fuse disconnect above it, that becomes a combination starter. It has the combination of both contactor, overload, and overcurrent built into it. Across the line starters, main base, you've got a contactor that applies full voltage to the motor when it's activated. Bang! Okay, and where we saw with the previous, the curve of the motor, we're up to 500. It could be, depending how good the power supply is, up to 6 times operating current. So the motor comes up to speed as rapidly as the motor starting torque can overcome load and inertia. So very quickly, typical centrifugal pumps, even a fairly large one, we're talking 2 seconds, smaller ones, half a second, bigger ones, under 10 seconds, fairly quickly. Now, further with starters, there's 2 different ways of rating them, depending on the standard. Okay, and appreciate that a contactor and an across-the-line starter does see high starting current. And when it opens, it's with the opening of points, and afterwards you turn the motor off, it tends to want to strike an arc. So across-the-line starters do see fairly heavy use. In the United States, an organization called NEMA, National Electrical Manufacturers Association, developed sizing for starters and contactors that assumes operation with the worst case applications. In Canada, EMAC, at one time it was called CEMA, Canadian Electrical, but then they changed it EMAC. Why? Because they felt it was a good idea. Electrical Equipment Manufacturers Canada. Basically, it's the same standard as NEMA in the States. And under NEMA, contactors and starters, which use contactors, simply have the maximum horsepower rating at each size. In other words, a 208 volt, you can see a size 1 starter, 7.5 horse, up to a size 4, which is quite a bit larger, is rated 50 horse. At 600 volt, you can see the ratings that are standardized. I haven't got them here for 480, but they're easy to find. And just slightly below what the 600 is. Now that is NEMA or EMAC. There's also IEC, utilization category, sorry. The European organization IEC, Electrical or International Electrotechnical Commission, developed ratings for starters that is based on the type of application, ranging from AC1, which is heating loads. There's none of this inertia or inductive situation that is where you're getting that high current from. Slip ring motors, you can see it. AC3 is common to what we're dealing with. AC4 is where you're partly in the process of starting a motor and then try to break the contactor. You don't see much of that. But starters will be rated for basically AC1 with a correction factor. The fact of the matter is NEMA EMAC is sized for worst case, so it provides good starter contactor life and a good safety factor in most municipal applications. NEMA size starter contactor momentarily withstand approximately 400 times the current rating. They are tough. By comparison, an IEC rated starter contactor can momentarily withstand approximately 30 times the current rating. They are a lot cheaper because basically it's a smaller contact that, because of the AC1, has a higher rating. People will, and even going to AC3, the rating, they still are smaller than what the NEMA or EMAC units are. And they have a nasty habit, if they see high currents, of welding the contacts together, in which case when the overload says disconnect contactor, it can't. So please don't use them. Now let's look at interesting stuff. In place of an across-the-line starter, which is hit and go, full voltage, we have solid-state soft starters. Now, at one time, along with that, of course, is across-the-line starting, is very high current rush. And at one time, it was very important, still is, that we get rid of that. We reduce that down to something. The utilities don't like it. Somebody starts a motor and everybody's television starts showing funny things, okay? So back in the day, before electronics became so dominant, there's different ways of doing that. You would start the motor first or take it up to whatever speed it could with a primary resistor, a primary reactor, a Y delta, a part winding was the system, or auto transformer. Auto transformer was and is the best of those type non-electronic systems. And with an auto transform, basically what it is a transformer hooked up. It's not purely isolated. They have one of the leads common across from both the supply side and the utility side. What it does is basically transform the power down, and with a centrifugal pump, because all the action happens as speed comes up. The ideal setting was around 65%. They had taps at 50, 65, 75, and something like that. But 65 was the ideal one. And using that, so you're starting the motor at a reduced voltage of 65% and give it there a few seconds, and then with a timer, boom, you go across the line. But the motor is already a fair bit up to speed. So the power peaks that show up when you first started at low voltage and when you flip it to across the line voltage are roughly equal, and it'll essentially have the starting inrush current. In other words, instead of 600 times, it becomes 300 times. Then along came electronics. And basically what they do is chop up the output sine wave, okay? Allows you to ramp up the motor in a controlled voltage by adjusting how much of the sine wave is carried through and how much is cut off. Appreciate the big advantage of soft starters, besides being adjustable and everything else, is the fact they can also soft stop. It can play the same game that it used to start the motor, increasing the voltage. It can help power it down slower by decreasing the voltage when you want it, okay? Here's a neat little thing that shows what's actually happening. That's fairly quick ramp up or ramp down, but you can see we start off actually the right now, and then it falls back to the point it allows more and more and more to go through. And this particular thing is called phase angle control. Works by modulating a triac or whatever, a device that you can control, send a signal to, and it'll control what gets through. Gate diode-like devices delay the cycle conduction only until a predetermined portion of the wave remains. So you can control how much of that wave comes through. The frequency does not change, and the motor accelerates or decelerates slowly only because of slippage due to reduced voltage. Solid-state starters are not variable speed. They are reduced voltage starters that have their benefits. So biggest, number one, they're more controllable. Number two, they can do a ramp down, which is significant. Okay. Now for pump applications, using a solid-state starter, you want a class 20 overload, because a class 10 with that drawn out voltage effect, the currents, although they're not as high as you would across the line, they're there and they last longer. So you want a class 20 overload. And ramp down time should be limited to about 30 seconds, simply because you are heating the motor. That motor for 30 seconds is seeing a reduced from across the line to a lower and lower voltage, therefore it tends to heat. Now, if you're using submersibles, the ramp down time should be 3 seconds, and we'll get to that later. Not because of electrical, but because of mechanical things. Submersible motors have thrust bearings built into them. As I said, they're not a replacement for adjustable speed drives. Since ramp down time should be adjusted to be twice as long as ramp up, ramp down is where water hammer occurs. Suggested maximum ramp up time should therefore be half that, 15 seconds. In pump applications with a relatively high head to low capacity ratio, they can be very effective in minimizing shutdown water hammer. I've seen it where even a few seconds of ramp down on some systems will make all the difference in the world, and water hammer virtually disappear. Now, with solid-state soft starters, the high-speed switching devices are no longer really required. In other words, once it's done its job, the solid-state devices aren't doing anything, but they do consume some voltage of their own. And the amount they consume is basically a watt an amp a phase. Let's take our classic 100-horse motor at 600 volt, which means running it is pulling 100 amp. So we've got 3 phases, so we've got 300 amp, which is 300 watts of heat. Okay, so what we do is once the unit has come up to speed, we can have a bypass mechanical contactor, so straight on-off contactor, close that and essentially short out the solid-state starter so it's not doing anything at all. Now, if you put an overload, which you should, on that bypass contactor, effectively, contactor plus overload, you have a motor starter, which with the rate controls can be used in an emergency. In other words, if the solid state starter for some reason fails, and you've done that with the bypass counter and you got the rate controls, you can actually run the motor across the line using that. Because that happens so seldom and it's not normally being used to start the motor, then you can go to an IEC AC3 contactor and save a few bucks and save a little bit of space, because it's not doing anything very significant. Power, and if you look at this drawing, what we're talking about, you see coming right down the center, you've got a motor circuit protector because the starters have built-in overloads. Okay, so you've got that going straight down line. You've got the starter, which is your control and overload in one unit feeding the motor. Off to the left, because we don't want that 300 watt with a 100 horse motor, off to the left, we've added a bypass contactor with an overload, therefore a starter on the left-hand side there, and in an emergency, we can use that to start the motor. Of course, the motor is bang on, power disconnected, bang. Another thing that is typically added, power factor correction capacitor, and we'll get into that later, why we have capacitors. They're used to improve the power factor of the motor, and again, we'll get into the whole deal later on. The problem is capacitors don't like quick changing current, which is basically what that solid state starter is doing when it's ramping up or ramping down. Therefore, it will take out the capacitor very quickly. Solution is to have another small contactor on the side that basically stays out of the game until the solid state starter says, okay, I've peaked out, hit the bypass contactor, hit the power factor capacitor contactor, because of course, as soon as as the two of them come in, we're basically taking the soft state starter, solid state starter out of the equation, and the power factor capacitor is happy. Same thing on ramp back. We disconnect that first, and then ramp this thing down, and that can be done. Now, this is all great fun. It serves two purposes. One is to say the solid state starter will do a nice job of ramping up the voltage, which ramps up the current, okay? And in fact, reduced voltage starters are required, BC Hydro, anything 50 horse or greater. Again, the effect of this stuff on nearby residents and whatever. Solid state starter, you can actually set to what the current limit on the motor starting will be, 300 being a typical setting. So again, on our 100 horse motor, which across the line, 500-600 amp coming in, you can set it at 300%, and it'll say fine and dandy. At that 300 amp, we'll control it 300 amp, and it just does it. Now, the ramp down, as I say, water hammer on pump starting is usually not an issue because the liquid in the lines acts to retard acceleration. So people say, oh, you turn the pump on, you're going to get a shock wave. Actually, it's really more of simply going to the shutoff head of the pump and then, dissipating down from there. It's not that. But shutdown is a different ball game. And this is where, as I say, between mechanical and electrical, holistic is important. Looking at these curves, let's say the first sketch we have, call it left upper. Basically, there's our system head curve. There's the pump, there's the force main, and it's discharging on the right-hand side at that elevation. Now, when a pump is operating, it will raise the pressure, that vertical red line, it's raising pressure, and then friction to above the static head, and then what's above that is actually compensating for the friction of moving the fluid, and there you go. Now, if we turn that pump off with no power going in, the hydraulic grade line can fall down. And as you see, hits a point where I've got separation. If it falls below, significantly below the force main, you will actually get column separation, unless there's air vents or something. Basically, what's happening to the left of where it says separation, that load, the inertia there has stopped the flow from happening, and you've got it right there. And then the other piece has gone on because of inertia, and you end up with an air gap between the two. You got a water column to the left going down to the pump, and you got one to the right going to your discharge. You've actually pulled a vacuum in there. That, assuming the pipe can take the vac, that is no big deal. But then eventually that vacuum will stop the discharge to the right and suck it back, atmospheric pressure pushing it back, and you've got nothing between to damp, unless by some miracle you got an air release valve that's brought in air. When those two ends hit, bang, you've got a real good spike and force mains get broken, and I have seen the results of that. Why did a municipality end up with about 5 or 6 breaks at one particular point on the line? Because that point was literally like this. It's sort of almost to the peak, but where you've got that situation, and the pumps were shutting down too quickly, and there you go. Now, when you've got soft stop, using a solid state starter, and you got soft stop, you actually can apply energy to the force main as you're ramping it down. Therefore, the line comes down nice and steady, and as you can see here, once it hits that point where everything is nicely stopped to the elevation, then you can turn it off because there's no fluid flow and everything's great. We've been through that, so let's move on to the next item, which is the higher the static head to friction ratio of the force main, the faster water column deceleration will occur. Appreciate with solid state starter motor application, heat buildup is significant and ramp down time should be limited to not more than 30 seconds. In other words, we can play this game for 30 seconds. I'm going to make a comment, by the way, going back to the previous drawings here. If your force main goes down and then up to the discharge, your chances of having water hammer from separation are minimal, okay? But as I say, the solid state starter can apply energy on ramp down, which will control how the discharge head comes down. But you're limited to about 30 seconds. So if you've got something that is going to come down quicker than that, the solid state starter with ramp down will make a heck of a difference. Now, I mentioned they are not variable speed or adjustable speed drives. Let's talk about adjustable speed drives. And again, this would be replacing your standard across the line starter. Because changing the rotational speed of a centrifugal pump has a profound effect on pump performance, remember the affinity laws. Capacity varies as velocity, head varies as velocity squared, and horsepower varies as cube. Various means of accomplishing this, in other words, controlling the speed of a pump, have been utilized over the past. And here's some examples. Hydraulic coupling, like essentially a torus member, which is like a fluid coupling, but not a torque converter, which the amount of oil in it can be varied. That will adjust speed. Wet clutch is simply two clutch plates riding in oil with the pressure being controlled, and of course that generates heat, etc. Eddy current couplings, which in my day was the most common way of doing it, essentially a rotor and stator motor, which had control. You controlled the voltage applied to the rotor, and that controlled the slippage of the motor. And of course, heat was built up while you're playing this game, but it did give you variable speed through slippage. All of these basically are doing by losing the energy between the two speeds. Wound rotor motors, different type of motor, same type of control. Magnetic coupling, two steel plates and a permanent magnet in between. I remember somebody were offering this, and some of the saw, oh, this is the greatest thing since cornflakes doesn't have electronics. Yeah, but then along came another way of doing it. All these systems were the same in as much as they utilized slippage to control the speed between a constant speed motor and the pump. Slip speed. Power loss is proportional to the slip speed times operating torque and appears as heat loss. With a centrifugal pump, that means that about 10% of the rated motor horsepower may appear as heat. You can kind of imagine a 100-horse motor, that's 10 horses just going into heat. Another means of controlling pump speed was through the use of belt drive, with one sheave having spring-loaded faces and the other where you could the sheave size could be just. The equivalent to that is the I'm looking for the word that is used in some constant speed transmission, where basically, again, they use a linked steel belt. Same idea, you're changing the two pulleys. At one time, as I say, there was a device that did it using a rubber pulley, and that was great, but it really was intended to be manually changed and then left there for a while. As we're talking here, another controlling speed, okay? Very similar to continuously variable transmission. That's what I was looking for. Read my own stuff. While relatively efficient, the system is maintenance prone and intended really for manual control. Then along came electronics and changed the world. Very important. PWM, pulse width modulation. How do these variable speed devices work? Well, here's what happens inside. The first thing they do is the incoming AC power is rectified to DC. You see these little arrow things with a plate on them? They're diodes. A diode has only two connections, the top and the bottom in this case. And what a diode does is allow power to only go one direction. So what they basically do is the sine wave goes back and forth. It simply picks off the part that it wants and converts that AC into DC. And isn't that a miracle? And my God, but we don't have to deal with that. You've got a car with an alternator. That's how it works. Kid you not, that's what car alternator works. The AC frequency varies is how you rev the engine, but it has diodes in it, the alternator, which flips it all to DC, and there you are. Now, in our case, let's go back to variable speed. Now we've got DC, and on the other side of the DC, and a capacitor thrown in to dampen a few things out. On the right-hand side there, you've got those vertical double plates. What that is, with a little tab on the left, what that is I call them track. In other words, a 3-connection device, which basically you can control. So we rectify AC to DC, then we invert it, which means we flip it back to AC by the way we pulse the DC power. And we'll see that in a minute. And by pulsing it, basically we can control what the motor sees. And it can be considered a variable frequency, variable voltage output or power source. Okay? And nearly any conventional induction motor can be powered from this type of drive. Not all applications are recommended, but basically the motor's quite happy with the different frequency and voltage that it sees. Let's get into that a little deeper. As I say, basically it's rectified, the AC becomes DC, and on the output side, the DC is flipped first one direction in short little pulses, but you notice short little pulses one direction, then flipped in short little pulses the other way. And as you see, the lines get wider until the middle, then they start getting smaller again. What the motor thinks it's seeing is shown by that sine wave. Okay? And we're on the left-hand side, the difference, we had a full cycle was 60, giving us 60 hertz on the input, 60 cycle at 600 volt. On the other side, the sine wave thinks that it's seeing 300 volt at 30 hertz. Usually the voltage varies as the frequency. Motors are happy with that, okay? Now, let's animate it. Isn't this pretty? Okay, you can see when there's nothing, then it gets virtually, when there is no gap, so to speak, column, then you get nothing, but as the column gets wider and wider, the voltage gets higher. And that's what's, right now you hear the motor speed, that's how you're controlling it. And again, to give you a better idea, at the top, that's the raw output of the drive. At the bottom, not at the same frequency, unfortunately. At the bottom, if you put a filter in, like some sort of induction load in between, that's what the motor thinks it's seeing, is a variable sine wave at a variable voltage and a variable frequency. It's the variable frequency, of course, is giving you the ability to control the speed of that motor. These drives have different names. Adjustable speed drive, which is what we used as the ISA, Instrument Society of America, designated variable speed drive, variable frequency drive, inverter drive, pulse width modulating drive, whatever you call a horse, it's a horse. And originally, I remember when they first came out, they were unreliable, they were large and extremely expensive. But guess what's happened with electronics over the years? So nowadays, it's become much more practical than it used to be. Used to be the consideration that if you walked in and looked at the equipment cost of a pump station, if you went variable speed, consider you were going to add 50% to the cost of it. Now the cost of it, something below 5%. It's not a big deal. Another little benefit, neat feature of, let's call them adjustable speed drives. That's what I'm used to. One of the nice things about these drives is you can use them as phase converters. The input is rectified to DC. The output is AC, a simulated AC. Realize if you oversize the drive by about 50%, you can have only 2 of the incoming lines, okay, which is single phase, and it will rectify that to DC. And by being oversized slightly, even though the current goes up, it's a happy camper. So your single phase coming in becomes AC on the output side. And you can use it as a variable speed drive you were before, or if you want to use it as a phase converter, just simply set the output at 60 cycle, and away you go. Because of that ability in the commercial business industry, like buildings, heating supply, HVAC, The ability to control the speed of a small three-phase motor from a single-phase input has all but limited two-speed and voltage-controlled motors. Back in the day, that was quite common to have two-speed motors or voltage controls of the resistor. That's pretty much been killed. You can get adjustable speed drives that will very nicely fit in the palm of your hand. It's been quite a significant thing. Now let's look at a couple of disadvantages. One thing with the drives, because of the pulsing on both sides, even the rectifying it creates pulses. You can get harmonics on both the line and the load. On the line side, it affects power quality, how good a sine wave it is. On the feeder side, it can result in voltage spikes that can actually damage motor winding insulation, particularly if the motor is a long ways away. What's a long way? Generally 15 meters, so call it 50 feet between the drive and the motor. Over that, you really get nervous. Smaller motors, having smaller windings, are more susceptible. So the smaller the motor, as I say, the more susceptible it is to this. Now you can use line filters, and anytime drives constitute more than about 20% of the load, certainly all pump stations, but even in a treatment plant, if drives are more than about 20% of the total load, then load side filters should be utilized for all 600 volt applications or lengthening motor feeds at 208. I say that because 600 volt or 480 is more susceptible to doing damage than the lower voltage. Like 208, normally you don't even bother with filters. So probably 240, same thing. Also at 600 volt, motors should have ISR, or inverter spike resistant wiring, advised. We'll get into that when we get talking about motors. Shaft voltage, you hear the talk about shaft voltage, and I'll let you read through all this and it'll tell you. Basically, the situation is, in most cases, you won't see it, but it can occur, and it's very difficult. To eliminate it is probably not worth the gamble. Now, let's take a look. What does variable speed do with pumps? Now, variable speed, unlike a soft starter, which is 30-second limited because you're playing games only with the voltage, this plays game with the frequency and the voltage. Therefore, nearly infinite ramp up, ramp down times. You want to ramp it up over a day, go for it. Therefore, superb water hammer control. Given their practicality, even slow-acting pump control valves in a lot of applications. I'm not a big fan of pump control valves, to be frankly honest. If you really want to control, a better approach is the solid-state starter with soft stop, if you can live with that 30-second limitation. If you can't, then you start looking at drives. Now, this is a big point. I've seen ads where they say, well, you're going to put on a variable speed drive and it's going to save all sorts of energy. Isn't that wonderful? Every time you use a drive, variable speed drive or adjustable speed drive, you're saving power. In some applications, in the right applications, they can be quite significant. But there are applications where it will cost you power. Okay? Affinity laws state that pump capacity varies with directly with speed. Capacity varies with speed, but that the head varies as the square of speed. Now, since we're changing speed, adjustable speed drives have far more effect on head than they do on capacity. So they should be considered adjustable head pumping rather than adjustable capacity pumping. Where the head seen by a pump is liable to vary significantly due to line friction or whatever, then adjustable speed pumping really makes sense. A lot of friction, variable speed will pay off. But if the total dynamic head seen by a pump does not change significantly, in other words, static head is quite high and not so much friction, then there's no real power saving to be made. Appreciate that an adjustable speed drive, due to losses through the drive itself and through the motor, due to the imperfect sine wave, involve an overall efficiency loss of about 5%. So you've got to, if you're gunning, you've got to make up that 5%. Realize too, if you're at high static head, low friction, and you try to control the capacity, you're essentially moving the pump away from best efficiency point. Application, once we're pumping up to a treatment plant and they wanted to control the inflow, which is fine, but it was all lift up to the treatment plant, very little friction. And the question came up, well, how much power are we going to save? The answer is it's going to cost you power. Face the facts. Here's an example where you got a lot of friction, low static head, good adjustable speed drive application. If you've got a lot of static head and very little friction, poor ASD application. Where's the dark line in between? Each case has to be looked at. Where you really should not use adjustable speed drive is high specific speed, i.e. drainage pumps. Because those pumps, if you look at the curves, can only operate over a fairly limited portion of their curve. So you really don't gain anything. You can't play the wide variations in flow or head. Another little trick, the low speed motors used on those pumps have poor power factors. And because of that, and the fact, adjustable speed drives, as we had with solid state starters, simply cannot be used with power factor correction capacitors. So if you try to use them on a drainage pump, you'll find that their very poor power factor cannot be corrected. You cannot put on power factor correction capacitors. So you end up with a very high current draw beyond what the normal drive horsepower rating could provide. In other words, if you can put capacitors on, you'd be much further ahead than you are by using variable speed, which prevents you from using capacitors. Now, however, an excellent application for adjustable speed drives is with submersible well pump motors. You'd think those little motors bad. No, good. There are some requirements by the motor manufacturer, but they're not terribly onerous. And if you put, say, you're pumping out of a well and put a level transmitter in there, you can set the controls up to provide a minimum allowable well drawdown level. And that is significant to a lot of people because the water that can be taken out of a well can vary. And this way you don't have to worry about over pumping it. The system will basically do it on its own. Now, one thing, beware of too quick deceleration for pumps using threaded shafting, like vertical turbines. If you set the ramp down time too quick, you can actually get to the point where instead of coasting along merrily, which vertical turbine pumps classically have done, they do their own thing as they coast out, and the motor being most of the inertia anyway. But if you slow that motor down, you got too quick a ramp down, and the drive will force the motor to follow it, unless you have the drive set up to turn off. If it can slow the speed of the motor too quickly, the inertia of the pump will take over and unthread the shafting. Then when you go to start the pump, it takes up that unscrewed with a hell of a bang, and you can do damage. Another thing with wastewater pumps, remember the thing that you have to worry about solids falling out at low speeds? So it's generally a good idea at intervals, say 2 o'clock in the morning, whatever, that you operate a variable speed pump at full speed if it's a sewage pump, wastewater, so that you can flush out the lines. Now, changing subject again. In the midst of all this, we talked about power factor. Okay, what is power factor? Normally, you've got voltage sine wave and the current sine wave, and they're the same, right? That's how they arrive. However, if you have a lagging power factor, then in fact the current sine wave will fall behind where the voltage is. Now the voltage one is leading. If you look at the voltage one here, this is the middle drawing, the minimum voltage there, if you look below it current, it's fallen back a little bit. Conversely speaking, if you have a leading power factor, it goes ahead. Now, what causes that? Any inductive load, typical induction motor, transformers, light ballasts. Nowadays you don't see so much because of solid state light ballast, thank God. Any of those induction things will cause current to lag. And a capacitor has the opposite effect of causing current to lead. Therefore, if you have a bunch of motors, it will cause the power factor to lag, and utilities will penalize you for that. They can sense it. Anything below 90% power factor, they will penalize you for it. You'll see it on the bill. So the motors have caused that. Well, how do we get around it? By having a capacitor in parallel with the induction motor, which improves. It tends to want to lead, the other tends to want to lag. You can bring it back up to within that 90% power factor. Okay. Now, how do I size these? So the easiest way to do it is to follow a chart like this. Okay, which is intended suggested maximum capacitor ratings for T-frame motors. We'll get into what that means. Don't worry about it. EMAC, electrical manufactured Canadian Class B motors, which most are, 600 volt and below. And a little warning, don't ever oversize the capacitors, okay? Because if you do, you will get over 1%, and that has its own collection of faults. So you basically pick the motor you're dealing with, pick the speed of the motor, okay, and away you go. Let's say we got a 100 horse motor at 1800 RPM, capacitor rating 30 kVAR. Will knock the line current down by 14%. So it has a distinct advantage. It saves you money by having that capacitor there. And in this case, 30 kVAR. They're rated by kVAR, and that's what it's done. And you can pick any motor, any speed, and it tells you which one to use. Use it, and you won't get into trouble. Now, what is this really doing? You can see at the bottom, there's a load of 100 kilowatt. Okay. As a power factor, if you go up to the top, power factor of 0.8, a lot of the power that's being drawn actually isn't being used. To the utility sees it, that 100 kilowatt, sees it as 125. So they don't like it because they're providing power they don't need to. So if you can reduce the kVAR down to 25 by using a capacitor, then the power factor improves to 0.97, and the utility sees it as 103 kVA, and they're happy campers. And here's the equation. Power factor is kilowatt divided by kVA. Kilowatt is kVA times power factor. In the classic one, kVA is kilowatt divided by power factor. Okay, a step simpler even from that. It's, say, pretend you've got a horse pulling a barge on a canal. You don't see that too often anymore, but there it is. The boat has to turn its rudder to compensate for the fact the horse is pulling slightly, trying to pull the barge towards the left bank. Okay, that rudder creates drag. So some of the power factor, or part of the horse, what he's pulling at, is not being useful. It's not actually pulling the barge forward. It's trying to pull it to the side, and you're having to compensate. What you're doing with power factor correction is having a more linear horse. Okay. We've been into what you do with solid state. Adjustable speed drives, there's nothing you can do with capacitor. They have features within it that sort of help. But anyway, what do you do across the line? There's different ways of hooking it up. This is the best setup. You can see your contactor, the two horizontal lines. The sort of hook thing is the symbol for an overload, and you got your motor. Put the capacitor between the contactor and the overload. And a lot of motor or starters are set up to allow you to make that connection. Therefore, two things. Number one, the overloads are sized directly to what the motor would be. You don't have to worry about power factor correction. What they recommend for, say, a 100 horse motor is the overload you lose. The other thing, the capacitor will only come in when the starter or the contactor of the starter is closed. Okay? Conductors, how do we move power? A conductor, a pathway for electricity, okay, made of conductive metal. Different ways of doing it. One is bus systems. Some people don't like them, some people do. I tend to like them. Basically, as you can see, it's a collection of copper bars with isolating pieces in between, put in a sandwich, and you connect to it. And what that is, with fairly compact system, you can move a lot of power. I'll tell you right now, the disadvantages, if something goes wrong with it, finding a replacement can be a problem. But man, they are neat, clean, and tidy. The other way, of course, is wire and raceway. Raceway conduit, for lack of better words. And wire can either be solid or stranded. The more strands you've got, the more flexible the wire. Real quickly with that, I wish I could show you an example I've got. I've got a piece of What really, in its heart of hearts, it says right on it's locomotive cable. You know, in a locomotive, the motors are down where the wheels are, and to connect them to where the power is being provided within the chassis of the locomotive is flexible. So they have very flexible cord, and it has conductors like you wouldn't believe, little tiny ones, relatively small, but a whole slug of them. Therefore, it's very flexible. That wire can be used and is approved for ordinary wiring purposes. And unlike conventional wire, which can be a bear to bend, this thing is actually surprisingly flexible because it has so many conductors. Typical wire sizes under Canadian Electrical Code, and I think you'll find NFPA code in the States, Electrical Code, you're not allowed to use anything smaller than 14 for any service. Below that, it's control wiring. So 14 is the smallest, and they get bigger and bigger and bigger and bigger and bigger as the numbers get smaller and smaller and smaller, okay, till we get down to 0. Then we start double zero, sort of like extra large, whatever, triple zero, 4-aught, as they call it, 2-aught, 3-aught, 4-aught. And then we get into MCM, which is actually defining what the wire is in terms of thousands of circular mils. Okay, don't worry about it. Just you need to know that 250 is smaller than 300, 350, 400, and you can go up to 2,000 MCM. Okay. The current rating of wire, of course, is related to the size of the conductor, but it's also related to the temperature rating of the insulation. For example, a number 6 wire with insulation rated at 60 degrees C is allowed to handle up to 80 amps of current, while the same size wire with insulation rated to 90 is allowed under code to handle up to 100 amp. Now, I always say the Canadian Electric Code and probably NFPA in the States, simple, one sentence: no overcurrent device is rated too low, no conductors too large. In other words, big wire with a low overcurrent device and they're happy. That's exaggerating a bit, but you get the point. In order to provide mechanical protection for conductors, they must be installed in something that provides mechanical protection. Conduits, rigid steel. Essentially what it is, it's like galvanized Schedule 40 pipe. It has to be approved as conduit, but basically what it is galvanized Schedule 40 pipe. It threads on the same, everything else. EMT, thin wall electrical metal tubing. Basically, you'll see rigid steel is allowed underground. Rigid steel is good if you're a situation like a pump station below a certain height, roughly standing height, where if a motor swings against it, you got some reason. EMT is thin. Use it where, in a case where it's unlikely to get hit. EMT cannot be used below ground. Rigid PVC, which is essentially approved Schedule 40 PVC pipe. It's glued together. Mechanical protection, not as much as rigid steel, of course, but it can be buried below ground, so that's very good. Also, for underground use only is what they call DB2 thin wall PVC ducting. Okay. Another thing is armored cable. An armored cable has several insulated conductors within a flexible wrapping of steel or aluminum or galvanized steel. Armor, basically the wrapping is doing the armor, and because it's done as it is flexible. Comparable conductors within a conduit. There's all sorts of armored cable. The common one in industry is called Tech 90, to the point that they almost talk about nothing but Tech 90. Okay. Now, with armored cable, you can move it around by laying it within trays, cable trays. And you see these in treatment plants. The nice thing about using that system is if you have several armored cables, if you decide to add something or change something, all you got to do is unhook it from the cable tray and put in what you're going to do or whatever. It gives you a lot of flexibility. And there's 3 different types: ventilated, solid, and ladder. Probably the most common being ladder. Now we talk about underground, and I mentioned PVC, rigid steel, PVC, DB2 ducting, Tech 90 cable are suitable for underground, not EMT. And the depth of burial is dependent upon provision for mechanical protection, which is in the electrical code. Uh, Point, the installation of conduit or ducting must be done under permit of a certified electrical contractor. You cannot have, and I saw this being tried once, you cannot have the electric or the general contractor put in conduit or ducting and then say, well, the electrical guy can pull in whatever, the cabling and everything, wiring. You can't have it. It has to be, the installation of that conduit and ducting has to be approved under permit by an electrical contractor. Uh, so there you are. Flexible cord. Flexible cord, also known as cab tire, is designed to allow, electrical equipment to be readily moved. Think like an industrial extension cord. Relatively expensive and applications are strictly limited. You can't use it the way you can Tech-90 cable. It is not a substitute for wire and raceway or armored cable. Now, 2747 relay. This, we're getting a little advanced here, but so be it. There's a IEEE standard for device functions. And basically, these are relays that serve certain functions. And what a 2747 relay does, number one, it's designed to protect for undervoltage. Typically, for example, if you've got a 600 volt and it sees the voltage drop to 540, that relay will trip, either open or close the contact. Mostly open so that it's fail-safe. Phase unbalance. If it detects that the power supply voltage amongst the three leads is unacceptable, a variation of up to 5%. Now, in each case, you're measuring between two leads. Say, talking about here, say voltage between 1 and 2 is 625, between 2 and 3, 630, and between 3 and 1, 575. The average is 610. Therefore, the unbalance is if you take the average of 610 and subtract the highest and low, the 575, the lowest divided by the highest, at 6%. Your imbalance is 6%. Said anything over 5 is bad. So at 6%, the relay again will activate. Okay, so now you know what a 2747 relay is, which a lot of people don't. Enclosures. You basically mount electrical equipment enclosures primarily intended to prevent accidental human contact. As a secondary function, protect the equipment from damaging environmental situations. Each of the 4 listed organizations has their own enclosure standards, but the first 3 are nearly identical. And the common EMAC, NEMA, and CSA, which is an approval agency in Canada, Canadian Standard Association, their enclosures are all pretty much the same game. And they have type 1 protection. Indoor use only, prevents people from touching stuff and being electrocuted, minimal environmental protection. Type 3, again, accidental contact, provides protection from weather. Type 4 prevents contact, again, by accident, but also provides protection against hose-directed water, like you're washing something down. It doesn't have to be just rain coming down. It can come up at it with a hose. And by the way, type 4 qualifies as type 3, always qualify going up. 4X is the same as type 4, but it's made with corrosion-resistant parts, either stainless or plastics. Type C, different ballgame. We're providing protection against temporary submersion at limited depth. That becomes a big thing. And the temporary immersion, they tell you what depth is allowed. Submersible is what we're talking about. Now we get into another subject. Type 7, again, always provides protection against contact. Explosion-proof design, meaning that if a blast occurs within the enclosure, it will not rupture the enclosure, and escaping gases are cooled to the point they will not trigger an explosion within the surrounding room. And that is something, again, we'll get into in a bit. Type 12 provides protection against accidental contact, provides protection against dust and light splashing for indoor use only. So type 12 meets the requirements of type 1, and there's the bunch. Now, IEC does things a little different, because they do, and they use a 2-digit way of identifying them. Basically, the first number, IP, enclosure and type, basically the 0 means ingress, none. It's
what it's doing is almost nothing. IP1 means you can't get a hand inside. IP2, you can't get fingers inside. IP3 tools, 2.5 millimeters or larger, tools a meter smaller. You see how it's getting smaller and smaller. IP5 limited dust, IP6 it's sealed, no dust. Now that's how accessible it is, from boy, you can electrocute yourself easily to you can't even get dust into it. The liquid is the second digit, ranging from no liquid, has to be dry. Vertical dripping, up to 15 from vertical, light spray up to 60 degrees from vertical, light spray any direction, low pressure spray any direction, strong pressure spray any direction, brief immersion, we're getting into semi-submersible, 8, continuous immersion, fully submersible. In general, certain types of EMAC, NEMA, CSA, and IEC enclosures can be considered as equivalent. For example, a Type 1 EMAC, NEMA, CSA enclosure is equivalent to IP20, which is defined the liquid, none, and first is the access to it. And I'll go back just so you can see that. IP22, you can't get your fingers in, but no particular liquids are covered. And you can see Type 3, you see all the equivalents, okay? And as I mentioned, a lot of them are usable. You can have more enclosure than what you really need, and it's okay. One very good way of dealing with electrical equipment is a motor control center. In the States, they spell it CENTER. Anyway, and it can be compared to a collection of filing cabinets with some smaller electrical equipment in drawers having rear stab connectors to automatically connect to vertical bars. Here is one of those quotation mark drawers, unquote, shown pulled out, and you're looking at the back side of it, and you see it's got little spring-loaded tab connectors that go onto bus bars, which is a copper or aluminum bar. Okay, in this case, a vertical bar. Motor Control Center will have both horizontal and vertical distribution bus bars, which distribute the power and allow devices like this to connect to it. And as I say, with smaller stuff, you can have breakers can be done. Some small motor control can be done simply as a drawer. You pull it out if you want to service it, you slide it back in, and away you go. There are wireways provided along the top and bottom of the MCC so you can bring in power and serve the motor. And on one side of some, because if you've got several starters or whatever, you need to get to the bottom so you can just go carry on to where your motors are. Here's a picture cutaway of a typical MCC. And you notice there's space along the top for bringing in wires. There is horizontal buses, which is number 9 on this thing. You can see those horizontal, the back there. Look at the middle enclosure, look at the back. You can see these horizontal buses, and connected to them are vertical buses. So each one, the top one will connect to the one on vertical on the left, middle one, the one on the right will be connected to the bottom one only, okay? And those go down, and as I say, a lot of these units can be slipped in as like sliding in a drawer. And there's space on the right of all these. You can see the one on the far right is open. You've got that big space that you can run wires all the way down to the very bottom right corner of that motor control center. Okay? Now, motor control centers are, the dimensions are pretty much standardized. Motor control centers typically 90 inches tall, 20 inches deep. The widths standard is 20 inch. Optional widths up to about 44 inch. The bus bars are located, the distribution bus bars are located halfway between the front and the back of the MCC. Motor control centers are actually designed that you can have starters on the front and the back. Now, in the typical pump station, you only use the front. You have no need to go to the back. But in treatment plants, sewage and water, where there's a lot of, and particularly smaller motors, you can have both sides of it being used. You've got sort of a walkway in between one or two of these things, so you can get at both sides of it, okay? So double-sided insulation. Where larger electrical equipment is to be installed, and here very often pump stations, but other things such as automatic transfer switches, solid-state soft starters, adjustable speed drives. For larger motors, the vertical buses are terminated and the full depth of the enclosure, the full 20 inches, is utilized. This, of course, results in a one-side-only MCC, and there is a picture of a one-side-only motor control center with a bunch of drives. You can see on each one of those at the top left, the disconnect, or pardon me, the breaker that's actually feeding that is a handle, so you can vary, and that handle is fixed. When you open the door, the black part stays put, and you can turn it off whatever you want. And what you're seeing down there is like an hour meter, the control for the variable speed drive, how you set it up, a bunch of options. And there's and at the bottom, fans to help keep things cool. Now, one of the interesting things we ran into as consultants is basically the project manager would say, okay, here's the electrical room. And inevitably, the electrical room, if we were lucky, was oversized. Okay, you could have a party in there. That's easy with putting your. If it's undersized, and that happened a lot, then you've got a problem. So we finally came down to a case of, look, what we should do is rather than say they're going to size the electrical room and we got to live with it, let's go the other way. You tell us what motors you've got, and we will tell you how big a room you need. Well, to do that, we came up with tables and motor control centers. And here again, you've got your basic, there's your basic widths of 20, 25, 32, or 44 inch. And for example, you got a 200 amp service entrance. The circuit breaker will take 6x, the XB, by the way, is 6 inches. So 6 inches vertical, 3 feet, 6 times 6, 36 inches. And the utility equipment, another 6x. So basically, the full height, and assume 815 millimeter or 32 wide. Into the bigger services, you can see you get a hydro pull. You actually, there are two sections: a hydro pull section at 510 millimeter, and again a metering section, service section at 815. And it just goes on and on and on. All those different things, and using those, you can very quickly size up what the motor control center is. And this is another slide that gets you into some other things: transformers, panel boards, starters, adjustable speed drives. From that, you can size it. From that, you can go back to them and say, based on the motors you've given us, here's the minimum. Okay, here's the minimum space that we need. And in terms of depth, there's a requirement, it's about 3 feet, I think. But anyway, that's the real big issue, is how much wall space you're getting. And they are going to have to provide it. Work much better. Another thing with electrical equipment, electrical kiosk. You're out in the field. You haven't got a building that you can put a motor control center in. So we have a kiosk. Type 3 enclosure, weatherproof. And inside it can be type 1 enclosure, and you can use electrical metal tubing because basically it's protected by the enclosure itself. Classically, single compartment, you can have one enclosure there, and all the electrical equipment is inside, the service equipment, everything. A little trick that you can pull with these, by the way, if you look at I'll get to that in a minute, you can actually have a compartment at each end whereby you can bring in air ducts. So if you have a below ground valve or flow meter chamber, you can actually have the fans and everything draw from the kiosk and discharge at the kiosk. Doing it that way, you don't have these ugly goosenecks above ground. Let me show you. There is a single kiosk. And as you can see from the left drawing, all the electrical metering, the incoming service and everything is there. But on the right drawing, you notice about halfway down on the left bottom and right bottom, you can see where we've got ducts coming into a chamber which has louvers on the outside. That way, as I say, the air for that underground chamber is coming from there, and away you go. And you can see the type of equipment that would be involved. Typical servicing. In this case, you're servicing nothing but instrumentation. Okay, but pump stations, submersible sewage pumps, and that you get into them. Now, but they're more commonly two-chamber. What does a two-chamber do? You basically have a front and a back. The back is used for your service and distribution equipment. The front is used for starter and control equipment. And that's your typical kiosk that would be used for, say, submersible sewage pumps. Okay, a 3-compartment enclosure has that, plus it has a fan at the end, similar to what we saw before on the single chamber. You had the option of putting in those little chambers that with a fan. In this case, it's a fan and junction box. It's taking up a full end piece at the end. There's a shelf in it. If you look at the drawing, you see there's a shelf just below the louvers. A fan on top of that is blowing down. Not shown here would be the service duct that again would come down at the bottom left of that, and that would go on to the pump station, providing forced ventilation. Okay. Also, in that duct, which would be typical 6-inch, 8-inch, whatever, you would have the cables coming back for the pumps, submersible pumps, that would terminate at connectors in that chamber below the louvers, and then through the wall and onto the starters that are inside the starter and control section. And another variation on that is a four compartment one, where in addition, you've got a washdown situation. You've got a spot where you can have a backflow preventer and a hose connection, so you can open that, hook up a hose, wash down the wet well if you want to. And that is the end of that section, and that's probably enough for now. Hope you've enjoyed. Thank you very much.